Hello everyone, my name is Pavel and today we're going to be setting up an EPU session. We're going to do the screening and setting up the data collection of one of our microscopes. The first thing we need to do is to make sure that on the microscope we don't have any cassette. Right now we do have a cassette, so that's why we need to take the sample out first and to load our grids. And for that we prepared another cap, and now we're going to be taking the cassette out. So when you see that the inventory button can be activated, check the temperature, press on it, and now carefully check whether you see the grids which have been loaded or you do not. In case the grid is not detected in the autoloader, it will turn gray, and if it is detected, it's going to be blue. And because I didn't load anything at the position number 1, you can see that right now it's being gray. If you see that the grid is not detected, the best is to stop inventory and to offload, to undock your cassette and to check whether everything is fine or not. The worst which can happen, the grid could disassemble upon loading or upon transfer on the stage, and there's a risk that it might end up in the column. So I need to be very careful with handling the grids, loading, and clipping those. Now you can see that the last grid is being detected. That means that the inventory is nearly done. All the grids which we loaded have been detected. Okay, so this is done now, and now we can start our screening session. You need to start the EPU if it's not yet running. I click on this label in the bottom, otherwise you can go to the main menu and then to find EPU. It might complain first that the column valves are closed. When you see this screen, you can in principle start the new session, or you could go to the 4 main tabs of EPU. EPU consists of 4 tabs. The first one is probably the most important. This tab contains all the settings of your microscope for different presets or different magnifications you'll be using. The second tab is a tab about it's the tab for actually screening and to collect atlases for each of the grid. Then this is kind of a tool tab which contains certain tools which you will use for the alignments of the microscope. And finally, the EPU tab will contain all the information about the areas which you will use for the data collection, areas of your grid, each grid. So first of all, we will go to the preparation tab and we will import the settings for the session. And I'll use my saved settings which will be useful for this data collection. There are different types of magnifications and settings which you might be using. Please talk to the Titan operator and figure out which is suitable for your data collection. In general cases, the magnification, in majority of the cases, the magnification you would be using and which is optimal for the data collection is 0.84 angstrom per pixel. If you go for, and if you're working with something smaller proteins, you might go for higher magnification. Okay, so I loaded the settings, and now we are ready to start creating the first Atlas session. I go to the tab Atlas, and then I click on Session Setup, and I click on New Session. Tasks. Are you sure you want to start a new session? We say yes, and now we need to decide where we're going to be saving our session. We are using Gatan K3 camera, and it comes with a server, dose fraction, and we will use, and I'll save the session in my folder with the current date. I will call it 2025 0724 PA, which stands for my initials. Select folder, we can click on set default storage folder, we can save it as TIFF, apply, and now we are ready to screen. If you remember, the first slot was empty, and we deliberately left it empty in case there is a grid on the stage, and there is a grid on the stage. So first we would like to screen grid number 2, so I select grid number 2, and I can minimize the window of EPU, and what we need to do now is to open the column valves, probably make sure that we have a grid on the stage, and for that I can just lower the screen using R1 button. It's grid inserting, you can see the beam, it's nearly well centered. And we see something, so we see the beam, everything is fine. We retract the screen, come back to our EPU session, and click on Start to start collecting the atlas. And first, what the system will do, it will take the grid which is currently on the stage, and it will put it into the position number 1. After that, when the stage is empty, grid number 2 will be loaded on the stage. This is all done automatically. It's a good idea though to check what's going on in this status message. Okay, now you can see that the grid number 1 is loaded to the position number 1, or its grid, the grid from the previous user is loaded to the position number 1, and now grid number 2 is being loaded into the cassette, or cartridge 2. That's how the clipped grid is referred to. So now you can see that the grid number 2 is loaded. Column valves are open now, and you see this message acquiring. You see the progress bar here in green, and on the right here in the status window you can see what actually is going on with the microscope. In the bottom you can also see the magnification which is used now. It's LM 135x. And you can see here the progress, and apparently some tiles are acquiring, and you can see also here that something is acquiring, but we are not seeing anything here. So in order to make sure that you see something, you need to click actually on this grid. And suddenly we see actually, yes, the EPU or the microscope is collecting the atlas of the grid of our interest. You can zoom in with a mouse, and here we see this grid, which is slightly damaged. Here you can see some ice, some blobs of ice, which is concentrated in the middle of the grid squares, which is probably due to poor glow discharging or insufficient. However, you should be careful with the glow discharging because if you're using carbon support and you have too intense glow discharge, then your carbon might be damaged. Actually, this grid doesn't look too bad. We can see quite a few grid squares which are preserved. They're not broken. And the ice looks quite good to me. Usually the optimal grid or the optimal ice should look like a gradient. So one side of the grid you will see very thick, and another one you'll see very thin, and then in between you would have some good ice. On this grid you can see that the ice is somewhat uniform, the distribution of ice thickness, and if you see that the edge of the grid squares is not very sharp, like it's rounded like here, and the more rounded it is, the thicker the ice you would be expecting. However, if it's too sharp, like here, probably the ice will be too thin, and you need to check very carefully if the ice thickness in this grid squares is optimal. If not, if it's too dry, you won't actually detect your particles, or they will not look nice. If you are sure that the ice quality is good, and if you are sure that you will not need to collect more data from this atlas, you can stop anytime pressing this button, and the atlas acquisition will stop, and that will save you some time if you are screening multiple grids. Just for the didactic purposes, we will continue and we will acquire the full atlas. Oh, this looks good. I like this area, and I'm quite sure that these grid squares are good for the data collection, if the sample is good. Sometimes you don't see strong gradient of ice on your grid. It doesn't mean you did something wrong. Grids which are frozen using Vitrobot often are not consistent, are not having the consistent ice quality, and the Vitrobot itself is not very reproducible. Therefore, it makes sense to freeze duplicates of grids. In our case, I can see that the top of the grid will have thicker ice. Here I see quite a few grid squares which are very thick, where the beam doesn't go through. So in a way, there is certain gradient. And probably this part of the grid will be thinner than this part. So anything in between might have good ice quality. Okay, so now the data acquisition is nearly finished. You can see the message, no more slots left to acquire, screening finished. That means that we have our atlas. What can we do now? We can right click and we can select export image, and we can save the atlas. I save usually the atlas using date. Today is 2025-07-24, and I put my initials PA, and I say this is grid. It's grid in the position number 2, and I can say position number 2, but it's actually grid number 1, which I loaded, so you need to be careful with your labeling. But I will call it grid number 1 because it's the first grid I screened today, and I add a suffix atlas. Return, it's saved. Now you see different colors which appeared. It's not because of saving, it's actually after the finish of the EPU session, and the software is trying to guess the thickness of the grid squares and to classify different ice into different groups. If you want to save this image, you can right click and select export image with overlay, and then you'll have all these colors as well. Okay, so the atlas is finished, the data acquisition, and you could have selected all of them, all of the grids, and one after another it would be screened. However, I do not recommend doing that because it takes much longer to screen everything. The most time-consuming process is actually taking the grid from the stage, putting it back into the cassette. What I find faster is to make a short acquisition of some tiles, and then to check how good the eyes and the sample is using this small data collection, and then to move to the next grid. Okay, so we go now to the tab EPU, and we create an EPU session. Before, we used an atlas session, so for all the grids. Now we need to create an EPU for each of the grid we would be working with. I click on New Session, and it asks, are you about to create a new EPU session? Do you want to use the preferences of the current session? That means preferences of the previous user. And if you know who the user is and you trust, you can say yes. And if you don't, you can say no. Doesn't really matter right now because you can always change the settings. I will say yes. And here it's quite a critical point. You need to set the settings of your session. You need to choose faster data acquisition. That will be the acquisition using office mode. And manual selection of your grid squares. We always save data which is coming from K3 camera as TIFF and non-gain normalized. So, and now I will save it to exactly the same folder I was saving my EPU session, and it's this folder. I say select folder, and in this folder my new session will appear. Set as default storage folder. That means that when you set the EPU session for the next grid, it will suggest you to save it here. And then you click on Apply. Okay, so EPU is quite a straightforward tool. It always goes, so you'll have lots of options in EPU, but the logic is going left to right and top to bottom. So in this case, there is nothing left to right, but we go top to bottom, and from after session creation, we have, and session setup, we have square selection tab. I click on it, and EPU suggests me to select the grid squares. First, I click on unselect all, and now I would like to select one of the grid squares which I find optimal. For example, I will select this one. Select. Now I will click once on Eccentric Focus button, and I will right click on the grid square, and I will select the option Move Stage to Grid Square. There are two types of options for moving your stage to the grid square. One is Move Stage to Grid Square, another one is Move Stage Here. If you click Move Stage Here, it will move the stage exactly where the cursor is pointing. I recommend to use Move Stage to Grid Square, then it will move to the center of the grid square. Again, we go top to bottom, left to right. There is nothing interesting right now in these options, and I'll go to the next one, which is whole selection, and here we go left to right. First, I need to do to determine the eccentric height at this grid square, and I click on Auto Eccentric Height. Now the microscope will determine the eccentric height at this grid square. After the eccentric height is determined, we will get an image of the grid square automatically. On the right, you can see the progress, and if there are any errors, they will also pop up here. We have this calibration outdated issue, but you can ignore it. Most likely it will not appear in other microscopes. You can see here that the image is acquired. You can see a nice grid square. So again, we go left to right. We don't need to click acquire because it's already acquired. What we need to do now, we can click on unusable square if we don't like this square, but I like the square, so I will then measure the size of the holes. And you can adjust it with the mouse like this. Okay. I measure the size of the holes, and then I need to click on Find Holes. EPU detected the holes according to the pattern of the holes which we determined earlier. We have here this option enabled, rename holes close to grid bar. If it's disabled, you will see that many more holes are selected, even those which are at the edges and outside of our grid square. How to deal with that? We have this option for filtering ice quality, and actually usually you might be seeing like bimodal distribution of the densities which are coming from this the image of this grid square. Either you click on remove holes close to the grid bar and it will select something like this in the center, or you can also play with this histogram and you can change it. Now you see this distribution, and you can select yourself how thick the ice or how thin the ice you would like to have in this selection. And you see that when I'm moving here, some of the holes might be rejected. So for this type of holes, probably this selection will be good enough. But you need to be careful because for the other holes you might have different ice quality. I do not recommend you to have any holes selected close to the edges of the grid bar, because the ice quality might be different, the ice might be not vitreous there. Okay, so right now let's go to one of the holes, and I can again say select move stage to location. Then the stage would be moved to the center of this hole. The next tab which I recommend you to go for the screening would be template definition. And first thing you need to do, again, you need to click on acquire. Okay, so previously there was probably a user who was just screening some of the grid squares, and we might be just inheriting the parameters from that user. What we need to do, we need to first of all center the hole. The hole was determined. You can see detected. You can see it with yellow circle around the hole. But now we need to make sure that it is centered. Now the hole is centered, and we can, if we don't like the exposure arrangement, we can say remove. We can right click on the exposures and we can say remove, and we can leave just one. So that's where the exposure will be taken at 12 o'clock. We can also set the defocus for this data acquisition, and for screening I recommend to use -3. And if you like to have more than this, you can add a bit more. Oops, I'm sorry, it was supposed to be here, acquisition area, and I'll select like 4 exposures here. You can select more, but for screening that's sufficient. And now what's also important is to set the autofocus. And I do not see, here. So it might be somewhere far away. I'll select autofocus exposure, which will be close to my hole. And then when everything is set, I can click on template execution and I hit the start button. So now you can see again on the right in the status window what's going on. So first, the microscope is trying to detect defocus, taking images close to the hole, to the selected hole. And it might acquire several images. And you'll see here acquiring negative and positive tilt images. You see autofocus succeeded, no stage delay needed. Then the microscope is setting optics to acquire the data. And acquire image, that means that the microscope is acquiring the images. And now you can see actually a nice sample here, with lots of particles distributed everywhere, and some particles are clumped, but some particles look like single particles. So I would say that this grid can be used for the data collection. You see a lot of ice contamination. However, this ice contamination can be easily excluded at 2D classification. So I wouldn't say that this sample is the best for the data collection. However, it might be sufficient, of sufficient quality if you want to check what it is. Okay, so if you are unhappy with the quality of the sample or the quality of the grid, you can come back to Atlas and select another grid, for example, number 3 or number 4, or you could say that, okay, I'm happy with this, and now I would like to collect a small data set or a large data set from this grid square. So in this case, you can select you can screen more areas or more grid squares or more holes in order to determine which one would be the best, what to use, which ice quality, and so on. We would need to align the microscope. We would need to make sure that the dose we are using is optimal. Probably dose is even more important to detect before alignment of the microscope, because that will determine your parameters for the data acquisition. And after that, alignments of the energy filter and gain of the camera. Once that is done, we would need to make sure that the image shift calibration is performed well. And finally, we will need to determine more areas where the data is supposed to be collected and to determine the parameters for the data acquisition. For example, the defoci you would select, or target defocus you would select for or range of the defoci you would select for the data collection. Okay, so first of all, I would start with the camera normalization with a gain and adjustment of the GIF after we determine the dose. And for that, we would need to find an empty area. For example, I'll select obviously bad grid square, for example this one, and this time I can click in the middle of this grid square and I can select move stage to grid square, or move stage here even. You need to make sure that you are at the preset of your data acquisition. So you go to preparation, data acquisition, and check which settings you have. The most important is to check your magnification, that you are imaging at nanoprobe and with the slit inserted. Once you are happy with these presets, with the settings, you can click on Set, and that will set the optics of the microscope to these settings. And you can click on Preview here. In this image you can see some lines in the area which is empty, and that happened due to the cryo cycle overnight, which led to heating up the camera, and we need to redo the gain. Now we have to refer to the Gatan PC, and here at the Gatan PC, the software, which is called Digital Micrograph, would allow you to measure your dose at the determined settings. First thing we need to do before we do anything else when we are at the empty hole will be to tune the energy filter and do the gain reference. Let's first, for example, do the tuning of the energy filter. So in order to do so, we would need to, especially for ETH Krios 2 microscope, we would need to go to a lower spot size. And in order to do so, we can check the button where we can change the spot size here. For example, in this case, to go down with the spot size, we need to press L3, or we could go to the beam settings and change the spot size to 1 or 2. You can see that the spot size has changed to 2 now. We need higher intensity in order to tune the GIF. Once you change the spot size, you can insert the screen and make sure that the beam is centered. So the beam is quite nice and round. We retract the screen. First of all, we need to make sure that the zero loss peak is centered. We'll click on it. Okay, here you can see the offset of zero loss peak, and after that, after you make sure that everything is fine, then click on Tune GIF. And it asks for either to do quick tune or full tune. You click on this button, make sure that everything is enabled in the full tune. You click on OK, and then you click on full tune, and then you just press OK. Tuning of the energy filter might take a while. And you can check the progress in the bottom. So in this image you see quite a strong gradient from green to red. The idea is you're supposed to be having a uniform color, closer to orange or brown. So now we see that the tuning has been complete. We click on OK, and the next step is to prepare the gain reference. For that, we go to the camera and prepare gain reference. We are already at the spot size 2 because we were doing the tuning of the energy filter, and if you're doing separately, then you need again to reduce your spot size. Now when you can see this message, you need to adjust the beam to 1520 counts, and I do that by spreading the beam with the intensity button. Okay, now it's good enough. I put I insert the screen to make sure that the beam is well centered. Center the beam. Retract the screen. Check the dose again and click on done. So now the gain and linear mode will be calculated. This will take a while. Now we need to press OK, and we will have to collect another gain for the counted mode. And for that we would have to reduce our spot size. I go back to spot size 5 or 6, maybe 5 even. And now you can see that the average count is supposed to be 15. I spread the beam again. And I need to make sure that it's centered. I insert the screen, center it, and retract the screen again. Check the count, it's 15, we say done. And now the gain for the counted mode is calculated. Okay, so gain reference has been successfully acquired. Click OK here. And now here you can see the gain, the image of the empty field before we collected the gain reference. Now you can come back to EPU and set again data acquisition settings. We click on set. That would set the microscope to our data acquisition conditions. And you can see here ready, and now we acquire an area of an empty area again, clicking on capture, and here we don't see these artifacts anymore. It's very good. Okay, the gain which we have created can be opened. We're using File, Open, go to disk C, Program Data, Gatan, and Reference Images. You can sort by the date modified, and you'll see the largest file, which will be your new gain reference. And you see here, actually, the size of the gain reference is 11K by 8K. What you can do now is you can click on Process and rebeam by 2. That would bin the gain by the factor of 2. Now it's 5.7K by 4K. And that would be useful for your processing later on. And also you might need to consider the orientation of the gain reference. Usually what we do in order to process data in CryoSpark or even in Reliant and to have it exactly the same orientation as the images or the gain which you produce a posteriori, you do process and flip vertically. Depending on your camera, you might need to do different types of flipping. For example, for Krios 3, we flip horizontally. Now, you can save this new gain as File, Save as in you select it as I don't see it here. I will select MRC format, and I will save this file as 2025 0724 gain. And this will be saved in reference images. Okay, good. We're done with the gain. Now we can go to another area where we will perform alignments of the microscope, and also image shift calibration. And because of that consideration, I would select a square which has certain features. For example, this one. I click on select and move stage to grid square. Okay, now it's very important to be at the eccentric height. We click on hold selection and eccentric height. So if the alignments are completely off, what you could do, you could go to Tune tab here, and then you could go to Alignments and File and load the latest alignments, which default alignments which have been performed. Let's do it anyway. Let's try to load the latest alignments, and I select all of them, using Control A, and then I point arrow, and then I click on Apply. And when I do this, I usually write down in my data collection protocol the data alignments file which I used. And together with this, I can also check out my apertures, and then I have condenser 1 aperture selected as 2000 and C2 aperture as 70. I will use objective aperture as 100, but that will be later on. In order to perform our alignments, we need to be at the eccentric height and in focus of one of the selected areas. And I will not move anywhere. I will still stay on the same grid square. I'll just select some carbon area, and before I start performing the alignments, I will click on eccentric focus to normalize the currents in the lenses, and just in case, I will go to auto functions and I will perform again the eccentric height. Okay, in the status you should see that auto-eccentric by beam tilt finished successfully. That's good. And now, as I said, I need to be in focus as well, and I'll get to focus. I can also reset the focus to 0 with R2. And now we are ready to perform the alignments. We are somewhere in the middle of this grid square. We are on carbon. We should have enough material to determine the CTF. Okay, so first what I would like to do, I would like to check the alignments of the C2 aperture. And for that, in the beam settings, I select the option 2 lens, which will turn off C3. I put the screen back, and now what I would like to check, I would like to make sure that C3 is off, and using the trackball, I need to center the beam in the center, in the center of the smallest red circle. Using the intensity button, I am trying now to go up and down, and to make sure that I see that it's actually concentric. And I would like to center the condensed beam in the center of the red circle. And right now it looks like it's relatively well centered. Now I spread the beam to the size of the second circle, and I want to make sure that the beam right now is centered around the red circle. Note that the precision of the centering will be limited by the precision of your centering inside of the smallest circle. And right now I can see that my C2 aperture is relatively well centered. In case it's not well centered, or if I would like to move it a little bit, I would click in the apertures tab on the adjust, and using multifunctions X and Y, I would slightly adjust the centering of the C2 aperture. When I am satisfied with the result, I will double check it with condensing the beam again to the center and repeating the exercise. So now I see that C2 is well centered, and I click on adjust again and come back to my normal settings of TEM and nanoprobe. Okay, so right now we are back to our normal parameters, and we need to make sure that the alignments we are performing, the direct alignments we would be performing, are done at our spot size and as close to our imaging conditions as possible. So first, what I will do in order to make sure we're back to our settings, I'll go to preparation, and again from data acquisition I'll click on set, and that would set the optics of the microscope to my data collection parameters. Okay, so now I would do very basic direct alignments, and those include beam tilt pivot point, and using multifunction X, I would try to minimize the movement of the beam as much as I can. Can also reduce the intensity if it helps. Sometimes it makes it a bit worse. And I do my best to minimize this movement. Okay, the same I do for beam tilt pivot point Y. Okay, and beam shift to center our beam with respect to the center of the green circle. Good. So you can check it once again with pivot points to iterate it once again. And it looks to me like it's already well aligned. Done. We insert the screen and we come back to our EPU settings. And now what has to be done in the auto functions, the next step would be to make sure that we do not have astigmatism. I didn't check my tone rings presets, that's why I will go back to data acquisition and I will run autostigmate in my data acquisition preset. We are ready to perform comma-free alignment, Autocoma. And again, I select my data acquisition preset and I click on start. We can see that Autocoma finished successfully, and we are ready to go to the next step. In order to perform the image shift calibration, we need to select the area where we would be able to detect certain features at different magnifications. And I would like to go to an area, for example, to this area. I would say move stage here, and ideally I would be in this area, but if I lower the screen right now, I am at my data magnification settings, I might be slightly away, and if I navigate, I will probably recognize some features, and that's good because these these recognizable features can be used for the image shift calibration. The most important though is to be at the U-centric height. So I will retract the screen and using auto functions, whole U-centric height preset, at the whole U-centric height preset, I will select option auto centric by beam tilt, and I'll click on start. It says auto centric by beam tilt finished successfully. That means that we can start the image shift calibration. I click on calibrate image shift in the preparation tab. And I can also select auto-centric here, but I will, because I did it using auto functions, I will just say acquire here. Yes, I want to proceed. That message pops out when the previous calibration was not stored. Usually it should not. Okay, this is our object. We can see that actually we find the same object at different magnifications, and the most important is actually image shift calibration between data acquisition and data acquisition preset and the whole preset. So can we say that this part of the IC is here? Yes, it's actually quite well calibrated. What we can say that maybe it's slightly a bit off, like here at this magnification. It's the same object, right? And in this case, it has to be upside down. It will be at this magnification, it will be upside down, and I think it's going to be somewhere here. Somewhere here, I think, or there. It should be somewhere here, I think. Yeah. And in this case, yes, and in this case, we are gonna be somewhere here. Okay, this is good enough. We can click on Store Calibration. And if you are unsure that everything is fine, you can click on Acquire again and check how good is your calibration now. Once again, image shift calibration is performed to make sure that the magnifications, different magnifications which will be used in setting up the EPU sessions, will be aligned with respect to each other. Okay, this looks good to me. We're done. We clicked already on Store Calibration. And if you are unsure, you can check it in the status, or you can click on Store Calibration again. So everything is fine. Well, we can come back to acquisition and optics settings and check once again what our data acquisition parameters. We decided that we'll have this illumination area, this spot size, C2 and C1, they're already set for us. We'll use the slit and the energy filter. This is the width of the slit, that's typical. We use 20. We use 40 fractions, that's also typical. And as we decided already, our exposure time will be 1.5 seconds. Now, if we set counted super resolution, that means that our data would be 11K by 8K. But if we have this option together with the binning option of 2, it will return normal size of the of the movies recorded at 5.7K by 4K, and we use this settings instead of binning 1 and just count it, because it speeds up the data collection by roughly the factor of 2. So we just need to set it up like this. Okay, so now what is left would be to center the objective aperture. And for that, I would recommend to go somewhere where you would see the piece of ice. Move stage here, because ice would allow you to see better the diffraction pattern. Okay, so now the most important part is to lower your screen down. If you don't lower your screen down, there is a potential risk that the beam might damage your camera. So when the screen is inserted, I click on diffraction button, and I can see a very nice diffraction pattern. When I click with my left mouse on this image, I can, with the mouse, I can scroll up and down to adjust the grayscale. I select the objective aperture, which I want to insert, and that's going to be 100. And see right now that the objective aperture is inserted and it's not perfectly centered. So in order to center it, I click on Adjust. I select my mouse somewhere in the center of the diffraction pattern, and now using multifunction X and Y, I'm centering the I'm centering the beam. I'm centering the objective aperture. Okay, this is done. And once you are happy, you click on Adjust again, and click on Diffraction button again. When we're coming back to EPU, we can lower the screen now. And if we come back to EPU, we need to still go back to our auto function, select data acquisition parameters, and to do auto stigmate again, because we moved the objective aperture and it might affect our astigmatism. Oh, right now we can see we're not on carbon, and actually this affects the precision a little bit, so let's go to carbon. And repeat it. Make sure that all your settings which you'll be using will be at exactly the same, all other presets will contain all the same settings. Data acquisition will have spot size 6 and illumination area 0.72. Go back to autofocus and it's exactly the same. The exposure time can be smaller, it will save you some time. And whole eccentric height, this is another one which will be constantly used during your data collection. It also has spot size 6 and a slightly different illumination area. Okay, so everything is fine. Now what is left? We need to select more grid squares and the holes in those grid squares. So I click on square selection, and I will not have a very large data collection right now. I will collect just a few grid squares, and I will select a few holes. I don't want to use this one where I was performing my alignments of the microscope. I will select probably something which will be close here, a few grid squares, Maybe this one, no, this one, maybe this one. And that's more than enough for my short data collection. Maybe I won't select this one. I'll just take these three. So in order to prepare now to find the holes, we can go to hole selection and click on prepare all squares. And that will allow to go one after another to different grid squares and to collect and to determine the eccentric height at each of these grid squares and to select automatically the holes where you would, according to the filter ice quality histogram, which we determined previously. Okay, now when all the grid squares are acquired, we can use the tool which is called selection brush in case we want to exclude some of the exposures or the areas where we don't want to collect our data. For example, if I don't like this, I can select, I can exclude these two. But to be honest, they are quite good, and in order to add them, I can click either add or to do control click, and that it will add them back, or control shift click will remove. Okay, and then the convenient part about that, we can go to now to previous square and to check exactly the same thing for the other grid squares. We can exclude areas which we don't like, previous square, and then we can also check whether we like this or not. So, and if you remember, I collected data somewhere close to the center, so I would like to exclude it. If we would like to exclude the whole grid square, and I'll show it to you just for the sake of demonstration, I can click on unusable square, and then you can see that I will have only two squares, 1 and 2. Okay, so now almost everything is ready for the data collection, and what we want to do is again to select where we would like to collect our data, and the last grid square we were at is this one exactly. I can go to square selection, and we are right now here, and I can click on hole selection, and it will turn out most likely that we are supposed to be already at the eccentric height of this grid square. So what I want to do now, I would like to go to one of these grid squares, for example this one, and to set up the test data collection. I go again, move stage to location of this grid square, of this hole, and using template definition, I click on acquire. Find and center hole again, and now it's important part for us to set the range of the defoci with which we would like to collect our data, and I go from -3 with a step of 0.2 micrometers, -2.4. I will use this range of defoci. And if I want to apply it to the rest of these exposures, I need to click on this button, and then you will see that the whole range would be applied to all of these exposures. And then we click on Add Acquisition Area, and that would allow us to expand our data collection to more areas. So now you can see here that we selected 700 exposures using this pattern. If we want to collect more data, we can select more of the grid squares. For example, if I would like to collect one more grid square, for example, maybe this one, it's also looking nice. I can say move stage to grid square. And with the hole selection button, I can add again holes, but I want to make sure that it's at the eccentric height. Click on Find Holes. And the software nicely determined the holes where we will do the data collection, and if I scroll down, I see an increased number of exposures. So we have everything here. We can start the data acquisition. Before we start the data acquisition, we double check all the parameters. It suggests us to perform diag gain reference acquisition every 1 hour. That is fine. Auto zero loss peak. We can also have it every 4 hours, or I will select every 1 or every 2 hours. It will do that. Also, it's often makes sense to save the atlas or save the areas where you will be collecting your data. So I will select export image with overlay, and I will add one more image here, and I call this selected areas. Click on save. Everything is fine and ready for the automated acquisition. Yeah, one more thing is in the preparation tab, it does make sense to now to click on export and to save our presets, which we will use for the data collection. Usually we have it Windows C, and then users, and then in the supervisor folder in the settings of EPU. I save it into my own folder. And I already have this file, which I saved in the morning today, but I'll call it underscore new. Save. And now we can start the automated acquisition. So you can see now that the microscope automatically goes to one of the selected grid squares, to one of the selected holes, and it starts to do the data acquisition. We need to make sure that the beam is well centered, especially when we start the data acquisition. Sometimes the beam is shifted, it's normal, and we need to check that everything is fine. After collection of several micrographs, it's usually relatively safe to leave it running. What is important to do now is to set up the data transfer, because the movies you're collecting, especially if you're collecting them overnight, might be very large. And I would need to set up a constant transfer of my data to the external server. To do so, I make sure that no one else has any drive mounted to the Gatan server, and I click on Mount my personal home folder, and this allows me to mount my storage, my temporary storage for the transfer of the frames. This is specific for ScopeM facility of ETH. So once my data is mounted, I'll see it here. And now what I would like to do, I would like to create a new folder here with today's date, 2025-07-24, and my initials. So inside this folder, I would like to now create two other folders. One folder will be the folder for the EPU data. This is the data which corresponds to all the areas where data will be collected, and also the data collection parameters, which is going to be stored in XML files. And another folder, which we will call the frames, is the movie data. First of all, we need to make sure that the constant data transfer is provided. For that, we will use a command which is called robocopy, and that's rsync analog, Windows analog of rsync. So we type robocopy, and now we will transfer the EPU data to the EPU folder. Where's our EPU data? Our EPU data will be located on dose fraction, and it's going to be in the folder which I created when I was creating the EPU session. And it should be in the folder Cryo-EM. I don't see it here. It's my folder, and it's going to be here. So what I can do, I can right click here and say copy address as text and paste it here. This is the origin, and the destination is going to be here. Right now it's empty. I do again right click, copy address as text, paste. And now I need to make sure that I'm performing robocopy using subfolders and using the argument MOT5. That means that it will be updating every 5 minutes. It's important not to use anything else, like we don't want to move this data, because if we move the EPU data, our EPU session will crash. But we want to move the frames data because we don't want to have large data on the Gatan server. That's why we have a separate folder here, frames. How to find the frames data? Go back to capture data, dose fraction, and now we select, we sort all the folders by date modified, and I select the latest one when the data collection started. And it's going to be this folder. I right click here and I copy address as text. I run a new robocopy. I paste this as an origin, and destination is going to be again home, frames folder. And this time I use again subfolders, and I use argument MOT5, so it will run this command every 5 minutes. And also I will add argument /move. It will remove all the frames from the Gatan server to my external storage. And I hit on return. And now you can see that all these images are being transferred here. Okay, very good. What else do we need to transfer? We also need to transfer potentially our gain. And as I said, the gain is going to be at disk C, program data, Gatan, gain reference images. I sort it by date modified, and I select everything which was coming from today. And I copy it, don't move it, you copy and paste it to the storage. Okay, so this is it. Everything is running, and I hope you enjoyed the tutorial. Thank you very much.